Welcome! This computer sitting next to me here is an Epson QX-10. This was one of the later CP/M compatible computers, and it is based on the Z80 architecture. It has 256 kilobytes of memory, and that memory is broken down into 64K that can pretty much hold the transient programs, another 64K where it can bank switch a BIOS, and another 128K for a RAM disk. It has two floppy drives. They are both 360K style floppy drives. I think they actually are able to get about 380K based on the sector size they use. I have replaced one of them with a Gotek already. Normally the primary drive would be on this side. I had to put my Gotek as the primary drive on that side just due to some cable length restrictions. So I'm able to boot this off of the Gotek, but I thought, wouldn't it be fun to add a hard drive to it? And there was actually a hard drive manufactured for this back in the day. It was called the Comrex Comfiler. Okay, so knowing that a hard drive had originally existed for the QX10, I knew it would be possible, but would there be enough resources on the internet for me to figure out how to do it? And there's not a lot of resources, and there is not, as far as I can tell, source code for the BIOS, but I did find some posts by a couple guys back in 1995 from Wayne Sung and John D. Baker talking about the IDE adapter they built for the QX10. So here Wayne says he built the adapter. This is on my blog. I've summarized their comments. So the old Comrex drive used a WD-1002, and this happens to be almost identical to the IDE protocol. So it's a few small changes. He summarizes the changes that he made, which were to add 1 to the sector number. So IDE starts at sector number 1, whereas the MFM controller, the Western Digital controller, started at sector 0. So we have to correct the sector number whenever we're talking to the adapter. And then we also have to explicitly request a 1-sector transfer. So with the Western Digital controller, when you sent the command, when you said read, for example, you would, as part of the command opcode, it would say whether you want to do a single sector or multi-sector transfer. IDE did away with that. IDE instead had a separate register. So you have to make sure to put a 1 in that register, otherwise it's going to try to transfer the entire track. And then he talks about eliminating some seek code. But anyway, this was easy enough for me to figure out. And he had a picture. I found this on the Wayback Machine. His website is gone, but there is a picture of the card that he created. I wanted to look at the original Comrex Comfiler. So Delta Don at VCF sent me some pictures from a friend of his, Gordon Owens, who had a Comrex Comfiler interface board. So a picture of it. Obviously, there is no hard drive controller on this. It did have a connector which would go to a hard drive controller. This may look like a 40-pin IDE connector, but it is not. It is just 8 data bits, some control lines, and some other signals broken out. It does have a data buffer, an address buffer, and some I/O address decoding. So I took that, and I managed to get most of a schematic by just looking at the picture, enough to figure out that it placed the controller at port 80. Once I knew it was on port 80, I went down here and I disassembled the QX10 BIOS, and I found all of the reads and writes from port 80. And I sort of commented out the disassembly. So we see here we have a 20 hex, and we write it to port 87. That happens to be the operation on the WD-1002 or on IDE. Either one is the same operation, but that does a read sector. 30 out port 87 is a write sector. And then way down here, 70 out port 87 is a seek. Yeah, so right here is the sector number. So here's where it writes the sector number. This is a 0-based one that we will have to correct and make it 1-based. So we can see it's doing all of the stuff that we needed to do in the BIOS, and where it does appear, just like Wayne Sung wrote, it does appear to be like 95% of the same things that you would do on an IDE controller. So I sat down and I patched primarily the seek routine. First of all, you have to put the Compactflash device or your IDE device into 8-bit mode.
So the 8-bit or the IDE protocol can be either operated 8 or 16-bit. It defaults to 16. So we need it to go into 8-bit. We need to do the add 1 to the sector number. That's right here. I added an increment. And down here, we need to set the sector count to 1 by writing a 1 to the sector count register. Also had to make a small patch to the write routine. So what it did is it sent the write command, and then it immediately started writing bytes to the controller. I found that the controller was not ready, so I had to inject a little loop in here into the write command where it waits for the controller to say, okay, I'm now ready for you to send bytes. Okay, here is the schematic for the QX-10 IDE adapter. So you can see over here we have the expansion connector for the QX-10. So this is what is in the expansion slots. And it has a lot of stuff that you would expect on a Z80 style computer. So you've got your address pins. We only need the lower 8 address pins. You've got your data pins, various read and write signals for I/O, for memory. Now it already has some logic inside of the computer that takes care of your I/O rec and your M1 and stuff to give you some nice I/O read, I/O write, memory read, and memory write signals. We've also got ground. We've got some power. There's also 12 volt plus and minus. We don't care about those. Reset line. So the first thing we need to do is we need to take these address lines and we need to decode them so that we can put the IDE adapter at a particular address. So we use a 74LS688. I've used this in several of my other vintage projects. What it does is it has 2 ports, 2 8-bit ports, and it outputs a low signal when those match. So we take 1, 2, 3, 4, 5 of the address pins over here, and we match them to a dip switch over here. So this lets us set a dip switch for the upper 5 address bits. We can set this so that it decodes at 0x80, which is where the Comrex compiler would be. The other pin that's important is the BSAC pin. That has something to do with the DMA. If the BSAC is asserted, then that means a DMA transfer is in progress. We don't want to be interpreting that as an IO read or write. So we take that and we also match on that being high. We've got a dip switch plus we've got pull-ups. That forms all of the address selection logic. Over here we have the Compactflash socket, and it has with it an associated data buffer. So we buffer all transfers to and from the Compactflash adapter. And the data buffer needs a chip select. The chip select comes from the address decoder, and then it needs a direction signal so it can know whether to buffer from left to right or right to left. So we get that from the IO read line. If a read is going on, then we want it going in one direction. If a write is going on, we want it going in the other. So that will connect the data bus of the Compactflash to the data bus of the Z80. The IDE adapter has 3 address lines that allow you to select any of 8 registers. So we just take those 3 lines from the Z80 going through a 74-144 unidirectional buffer. So Z80 address lines come in here, go through the buffer, go out into there. Same thing with the Z80's reset, and same thing with the read and write. That gives us full buffering on everything we send out here to the Compactflash. Compactflash has a chip select. We get that right off of the same chip select that we use for the address decoder. There's also a second chip select, which is used to select a second set of registers. We don't care about it. We can just pull that one up. There are some various signals that you'll want to pull up or down. ATA cell and C cell both go down. IO ready goes up. DMA rec goes down. Don't really have to worry about those. I think I did break out the interrupt line if you wanted to do something with it. Don't need to. I have the pin here, the DASP pin you can use to run an LED. So it goes out, goes to the buffers, and it can light an LED or it can light a plug going to an external LED. And then finally, I take all of those lines that hook to the Compactflash socket and I ran them down here to a 40-pin IDE plug with the assumption that we can then plug in an IDE drive or some other 40-pin device.
Okay, here is the IDE and Compactflash adapter. So down here we have the buffers. We have the data buffer, the 245. We have the address and control buffer, the 244. We have the address decoding chip right here along with its associated dip switch. Now what we want is the first dip switch off and all of the others on. Now different dip switches, you can flip them in upside down different ways. They could be numbered backwards, but the important thing to remember is this one all the way to the left here is off. All of the others are on. That puts the IDE controller at 0x80. This socket here is unpopulated, will be removed from future boards. That was for debugging. We've got pull-ups for the dip switch, an activity light, socket here for an external activity light, some resistors, socket here for a 40-pin IDE connector, and socket for the Compactflash. Now there's two different kinds of Compactflashes you can get. One of them has the mounting solder bracket here. The other one has it out here. To make this fit on this size board, I use the one that has it here. If you use the other style, you secure it down with a dab of hot melt glue or something. I will eventually come up with some bigger boards than this. This is the prototype. Anyway, that's it. It's a pretty simple, straightforward little board. Okay, now it's time to plug the card in. I think I can put it in any slot. I have been using this kind of second slot in from the end, so you just kind of line it up and push it in, and then make sure it's all the way seated. So it does have a little bit of a gap up here on this board because I had to trim a little bit off of it to get the cheap board. It had to be under 100 millimeters. But like I say, just make sure it's seated all the way in and you should be good. Okay, let's go ahead and give this a shot. I have plugged in the IDE controller and inserted the Compactflash card, and I have my Gotek set to boot boot floppy. We are booting up. We can see there are no hard drives yet. Now I've written a couple of tools to help in diagnosing things. So if we run disk pres, it will tell us whether the IDE board and its controller are present. So disk presence detector, it said done, so everything is good. If there was no IDE device detected, it would have printed out no controller, and if the drive wasn't ready, it would have printed out not ready. So that gives us kind of a basic test that the board is functioning. The next thing you can do is you can run disk info. And disk info will tell us some stuff about what the Compactflash disk is reporting. So this is not the CPM table, this is actually the metadata off the Compactflash itself. And it says it's got 1 F3 cylinders. Now these are of course in hex. It's got 4 heads and it's got 20 sectors. So again in hex, so it's actually 32 sectors. Now it's going to, the Comrex driver that's built into the QX-10 BIOS is going to expect there to be 4 heads and at least 17 sectors per track. So here we're good. If you did this and you had less than 4 heads or you had less than 17 sectors per track, then you would either have to adjust the geometry on the Compactflash or you would have to find a different Compactflash. Now to set this up, let's run a tool called HD part. So yeah, purpose subdivide hard drive, doesn't work with the older versions, preserve your data, yeah. So we look here and we've got one unrecognized system. That is because this Compactflash card came from a DOS system. It's probably got a DOS partition on it. So I'm going to delete that unrecognized system. And then I'm going to add a partition. Now it lets us choose between CPM 80B release, which is what we're running, Titan MS-DOS, which is for the DOS coprocessor card, or Valdocs 2.0. So I'm going to say CPM 80B release, and we'll give it 100% of the disk. We will exit, hit U for update, press the reset button to reboot. So we will do that. And you'll notice that it currently has no hard drives again, but what we can do is we can run the setup tool. And we can assign some disks. Hard drive 1, let's put it on drive F. Hard drive 2, let's put it on drive G. And then we can exit setup, permanent update. And I'm going to reboot now, and we should have our hard drive letters. So there, we've got F and G as drives 1 and 2. Now the way it always does this is when it was designed for the original Comrex compiler, it would take the 10 megabyte disk and divide it into 2 logical drives. That's why we have 2 drive letters. We have F and G. Each one of them should be about 5 megabytes. So if we do a stat on drive F, just under 5 megabytes. Stat on drive G, just under 5 megabytes. And these are both blank, there's no file. So let's copy a file. We're going to do f:/odyssey.txt a:/odyssey. And that is actually the first 400 lines or so of the Odyssey, which is the text file that I've been using to do my testing on this, because it's easy to have something you can actually look at and see if it is correct. So it is now on drive F. Drive F should now have about 16K less stuff on it. And there we are, typing out the first 400 lines of the Odyssey from the hard drive. So that consumes at least 2 tracks, so that's pretty much enough to prove everything is working, but we'll do a little bit more. I'm going to go to a different disk image on the GoTech. This image here has Zork, so let's do pip. We'll put stuff on drive G, and then we'll put a:****. Or actually we could just do a:***Zork ****. Should do that. Okay, we've copied it, so now if we do a stat G:, whoops, here, I don't have stat installed. There. Put the original floppy back in. Stat G:, we're down to 4550K, so we've used up like 300 kilobytes or so. Directory of G:, Zork is sitting there. Go over to drive G. Zork 1. There we go. Open mailbox. Take leaflet. Read the leaflet. Ah, yeah, Zork is a game of adventure. Let's go south. Ah. Yeah, we don't have a machete. Anyway, so we can play Zork. Thank you for watching my video. Please visit my website at www.smbaker.com for more electronics projects and sandrail stuff. Bye.